Okay, so today we are going to talk about combustion reactions and bond dissociation energy. So, first thing we have to do is learn how to balance a combustion reaction. Alright, so first things first. What is a combustion reaction? A combustion reaction involves a hydrocarbon or alcohols mainly and oxygen in the presence of heat. We'll just put energy, but really it's like heat. So this will always produce CO2 and H2O. So I'm going to write down an example, and we're going to go through the steps on how to balance it. So let's write the rules down first. So first things first, balance the carbons and hydrogens. It's easier if you do it in that order, but this always works. So balance the carbons and hydrogens. Sorry, my handwriting's a little rough right now. And do this on both sides. If at any time you need to write these down, if I'm going too fast, just pause it, write the steps down, and then replay it from where you're at. So step 2 is balance the oxygen atoms. And then we have step 3, balance anything else that isn't balanced. Okay, so now that we have these 3 steps, I'm going to show you an example with propane. We're going to work through this together, and then I'm going to give you another example that you can try on your own. And then I'll tell you to pause the video, unpause it, and then we'll go over the answer. Okay, so the first example that we're going to work on deals with propane. It's a common hydrocarbon that we use daily. So if you ever grilled outside and use gas, you're probably using propane. So propane is C3H8 plus O2. And then, like I said before, we're going to get carbon dioxide and water. All of this happens. So first things first, let's balance the carbons and hydrogens on both sides. So I always like to draw like a little line in the middle and then write down what elements I have on both sides. And then I start by just counting. So on the left side, I have 3 carbons, 8 hydrogens, and 2 oxygens. On the product side, I have 1 carbon, 3 oxygens. Do not forget this guy right there. And 2 hydrogens. So let's start by balancing the carbons. So since we have 3 over here, we're going to have to add on the product side first. So let's put a 3 there. This changes this to 3, and then our oxygen changes from 2 over here to 6 plus 1, so we have 7. So now we have to balance the hydrogens to make it even with the reactant side. So let's add a 4 here. It's going to multiply this to get 8. So we now have 8 of these, but you also have 4 extra oxygens. So Let's count the oxygens again. 6 plus 4 is 10. 10 is divisible by 2, so we'll be able to balance the oxygens on the reactant side. So let's do this. 10 divided by 2 equals 5. So that means we're going to put a 5 here, and then now we have 10. So the reaction is balanced. We didn't have to do anything with the propane. Sometimes you're going to have to, it just depends on the reaction. So you can see how simple that was, following those steps. So I'm going to let you copy that. Just pause it if you need to. Now, here's the example for you to work out. So example 2. So this deals with ethanol. I'm going to write that down. So I'm going to write this down. So C2H5OH plus O2. Let's make that a little smaller. Equals CO2 plus H2O. Alright, so pause the video and take a second to work on that. Alright, so here is how we're going to solve this. Same thing as before. You have CH and O, and then we also have CH and O. So let's start counting on the reactant side. So we have 2 carbons, 6 hydrogens, 3 oxygens. We have 1 carbon, 2 hydrogens, 3 oxygens. So again, let's start by balancing our carbons. So put a 2 here. This goes to 2. Then our oxygens goes to 5. And then let's balance the hydrogens and see what happens. So we put a 3 here. This goes to 6. But our oxygen now goes 4, 7. Okay. So let's see if we can balance this. So we have 1 oxygen there. So if we discount that, and then we discount the oxygen, one of the oxygens there. Actually, we don't even need to. We just have an extra oxygen there. So we have 2. If you just subtracted 1 from here, you'd have 6. So let's put a 3 here. And then we have 6 plus 1. That's 7. And this is balanced, because we have 6 plus 1 oxygen, that's 7. The reason I did the 3 minus 1 was because I was accounting for having an extra oxygen here to give us an even number. And then you just add the 1 back. It's just depends on how you want to do it, but this would be balanced. So if you need to go through the steps again, just rewind it. Alright, so that's in general how you're going to be balancing a combustion reaction. So we're going to go on because there's another topic with this. So we have types of reactions. And this doesn't have to do with anything in terms of, reactants or products. This has to do with the energy release. So we have 2 types of reactions. We have exothermic. So we have exothermic reactions. And we have endothermic reactions. Okay, so an exothermic reaction is when a chemical reaction releases energy. And that's not saying that it spontaneously happens. Maybe it needs a little bit of energy, but overall it's going to be releasing more energy than was put into the system. Hang on, let me fix this because that doesn't grammar right there. Okay. Endothermic reactions require energy before occurring. So we can say that it's a chemical reaction that absorbs energy before occurring. Okay, so we have these two types of reactions. Your combustion reactions are going to be exothermic. They're always going to release energy. They need a little bit maybe to happen, but they're always going to release energy. Think of a fire, an explosion, your car engine, same thing. So now we're going to talk about bond dissociation and the energy of calculating if it's exo or endothermic. So here's the formula for calculating this. Wow, can't spell tonight. So formula for calculating type of reaction. And this is just a pretty generic subtraction formula, but it's super easy. So final energy, I always like to just, I don't know if there's a real symbol for this, but I always just write EF, like E sub F, equals energy of bonds broken, which would be your reactant side, energy of bonds broken, minus energy of bonds formed. Obviously, when I'm saying bonds, I'm talking about chemical bonds. So I'm going to just, right here, put reactant side. And then this would be your product side. So how would this actually look? Well, there's a little thing right here I'm going to draw. This will help you kind of categorize this. You're going to get numerical values. So final energy, you're going to get a numerical value when you calculate bond dissociation energy. But this will pretty much give you, like, all these are tabulated values that you're going to be using. Alright, so let's do this in black. So you have negative energy. A negative value can happen. That means it's releasing, which means it's an exothermic reaction. And then you have positive energy, meaning it absorbed energy. So let me write this down and then I'll explain it. Maybe it'll make more sense. Exothermic and endothermic. Okay. So if we look at up here, we look at this formula. So we have final energy equals energy of bonds broken minus energy of bonds formed. So if you're really thinking about this logically, if it takes more energy to break your bonds than the energy of the bonds formed, you're going to have a positive energy value, meaning that it took energy to break those bonds to form your product. So that would make sense because it has to absorb energy for the reaction to happen, making it endothermic. If you have a negative value, that means that the energy of bonds broken was less than the energy of bonds formed. That means that you have to put less energy into the reaction versus the energy released when the bonds are formed. So that would give off energy. And that would be an exothermic reaction because it's releasing energy. So we're going to use the same reaction to calculate all this. We're going to use the same one that I had you calculate or balance the equation for. So I'm going to write it down, and then we're going to have a table that we have to copy. You're going to need about 9 lines on the sheet of paper. It's not huge or anything, but you do need enough space so you have all this info in there. Alright, so let's write the reaction down first. So this is for ethanol. I'm going to write example. Okay, so we have this. I'm going to write it balanced already because, you already did it. 2CO2 plus 3H2O. Okay, so here's our values, your coefficients right here. Alright, so we have our balanced reaction. Let's write this table down real quick. So you should copy this table down. You're going to need it. If you ever have like a test or something, your teacher should give it to you. I know I give my students this table because I don't remember all this stuff and be a little unrealistic. So I need a little bit longer. Sorry, this table's going to be a little ugly, but whatever. Alright, it's good enough. So draw lines for each of these if you need to. I just do it because the lines on the paper on the tablet are a little wonky. So here's this. Alright, so this table is going to be tabulated values for common bonds and the energy that is needed for forming them and breaking them. It's just a standard value. So let's write down the table. We have bond, and then the energy released, or energy, not released, just energy in kilojoules per mole. Okay, so let's write down our bonds first. We have hydrogen to hydrogen, or hydrogen gas. We have hydrochloric acid, or HCl. We have a carbon to carbon bond, carbon to oxygen bond, carbon to hydrogen bond, and then now we have a carbonyl bond, or a carbon double bond O, however you want to say it. We have oxygen gas, and we have an OH bond, which is common in alcohols, and you'll see those in carboxylic acids and stuff. Okay, so here's the energy. I'm not going to write the kilojoules a mole, it's already up there, but we have 436, 431, 347, 351, 414, 799, and then this one's 495 and 460. So if you need to copy that down, just take a second to copy it. Alright, so let's go ahead and figure this out. So if you've been doing this a while, you'll be able to just kind of look at what you got and figure it out. But since you're new at doing this, I suggest drawing out what you have on paper. So just draw the molecule. You have 2 carbons and an oxygen, so that's kind of our skeleton. And then here's our OH. You don't really need to draw the electrons, it's just the proper way of doing the Louis dot structure. Alright, so this is our alcohol. We have 3 oxygen double bonds, so I'm going to just copy and paste these because I'm lazy and don't want to draw more. Alright, so we have 3 of those, and then a little reaction arrow. We have 2 carbon dioxides. So let's probably copy and paste that. And we have 3 waters. And this might be easier for you to solve these if you draw it out. Simply because you can count all of the bonds that you have. Once you've been doing this a while, you don't really need to draw it. It's just kind of, you see it. Okay. So the way I like to do this is I draw a little line from the reaction arrow depending on how you're doing it. So what I do is I like to highlight the bond that I have that are different from each other on each side, and I write them down. So first things first, we have a CH, we have a CC, we have CO, and we have an OH, and we have O double bond O. Okay. Now, probably makes more sense to do parentheses for this part since that could be confused for electrons. Anyways, so now we have to count up how many CHs we have. So we have 1, 2, 3, 4, 5. So we write a 5 in there. CC, we have 1. We write a 1 in there. CO, we have 1. put a 1 in there. OH, you have 1. O double bond O, you have 3. So our reactant side is done. Now let's do our product side. We have C double bond O, and we have OH. Super simple. And OH. Okay. Let's do this. So we have how many of each? So let's do our parentheses and count them. So we have 1, 2, 3, 4. So we have, 1, 2. We have 1, 2. Yeah. Ignore what I just said. We have 2 in each of the molecules. So we have a total of 1, 2, 3, 4. So we have 4 C double bond O's. And then we have 1, 2, 3, 4, 5, 6. We have 6 of these. Now, since we know what all that we've got, let me do this in red also. Let's also label these so we don't get distracted. These are bonds broken and bonds formed. Okay, so now we have this part. We have to plug this into the formula. I'm going to copy and paste all this to the next page. Alright, so because we're going to need to use our calculator for this. So let's open that up. Alright, so first things first. Oh my god, let me move this out the way. Okay, first things first. Write down the values from the table next to this. So 414, 347, 351. Oh, wait. Yeah, 351. And then we have, where is it? 460. And we have 495. So in the calculator, what you're going to be doing is summing up both sides. So over here we have 799 and then 460 again. So what you're going to do in the calculator is the bonds broken side minus bonds formed gives you the final energy. So and then that'll be able to let you know if you have a exo or endothermic reaction. So let's do this. I'm going to write it down. So 5 times 414 plus 347 plus 351 plus 460 plus 3 times 495 minus 4 times 799 plus 6 times 460. Alright. So let's do this in the calculator. And then this will be the last thing we do. Alright, so we have one more thing to put in. Alright, so our final answer for this question should be negative 1243 kilojoules over 1 mole. So this answer means that we have an exothermic reaction. And that is how you calculate bond dissociation energy and determine the type of reaction you have. So if you have any other questions, you can refer to the PDF or you can rewatch the video.